Hello everyone, now we will discuss chapter 10, namely combustion in compression ignition engine. You can also call this diesel engines. This is the listing topic for chapter 10. The first topic will talk about the essential features of process in the compression ignition engines. As I mentioned to you in chapter 7, that the mixture preparation and the combustion process in the diesel engines is strongly coupled. We'll talk about these features and then types of diesel combustion, so direct injection, indirect injection, so we'll talk about this one. And then the next one is a diesel combustion process itself. Heat release rates analysis, so this is similar to the one in chapter 9. And then how do we model the diesel combustion process? So we'll take a look on this subtopic, so conceptual model of a direct injection diesel combustion. The last subtopic will be the fuel injection system. Okay, now let's take a look on the first topic, namely essential features of process in the combustion ignition engines. This is the essential features of the diesel combustion process. So firstly, the fuel is injected by the fuel injection system into the engine cylinder, and usually it is at the end of the combustion stroke, so just before the desired start of the combustion or the desired CA50 timing. And then, because this liquid fuel is injected at a very high velocity, so much higher than the velocity of the surrounding gases, which consists of air, residual, and maybe EGR. So because of this very high velocity difference, there will be a force acting on the liquid fuel that can break this fuel into small droplets, and this process is called atomization. And then this small droplet or small drop will penetrate farther into the high temperature and high pressure air mixture. So once again, this fuel injection is at the end of the combustion stroke. So the mixture inside the cylinder, which consists of air and residual and maybe EGR, are already at high pressure and high temperature. And then because of this high temperature surrounding condition, there will be a heat transfer from the mixture of air and residual into the fuel. So the fuel drop will vaporizes and it will form a fuel vapor. So in the end of this step, there will be a mixture of air, fuel vapor, residual, and maybe EGR. And then the compression stroke further move toward the top dead center. Then the temperature will further increase, and at some point the mixture of air and fuel vapor will ignite spontaneously. So in this step you can see the principal difference between the spark ignition and diesel combustion engines. So because of high pressure and high temperature, the mixture of air and fuel vapor ignites spontaneously, and this spontaneous ignition occurs after a certain delay period. So this delay period is the period between the start of injection and the start of the combustion. Then once a spontaneous ignition occurs, it will be followed by a further combustion process. There will be a release of the heat from the chemical process or from the combustion process, and then the cylinder pressure increases. And then the combustion process will continue consuming the remaining fuel inside the cylinder chamber. The consequent compression of the unburned portion of the charge shorten the delay before the ignition for the fuel and air. So this makes sense because of the high pressure and high temperature. So it will shorten the delay period. So this high temperature, high pressure also reduce the evaporation timing of the remaining liquid fuel. So it's mean that the fuel that is injected later will have a shorter evaporation time. And then the injection will continue until the desired amount of the fuel has entered the cylinder. And you will see later on that in diesel combustion engine, the amount of the fuel is used to control the level of required load. So in this case, the atomization, vaporization, fuel-air mixing, and combustion continue until essentially all the fuel has passes through each process. And then, uh, in addition, mixing of the air remaining in the cylinder with burning a gas or an already burning gas continue throughout the combustion and expansion process. So in this case, you will see that the fuel burning rate will be controlled by the rate at which this fuel will mix with air. That's why in diesel combustion, it's also called mixing control combustion. So this combustion process occurs under non-premix combustion, so or non-premix mixture. So because the fuel is injected right before uh, the piston hit the top dead center firing, and then it will mix right away, and then the combustion will occurs right after the start of the injection. So and there is a ignition delay there. So in this case, it is very well known that this diesel combustion is called non-premix combustion, and sometimes it's also called a diffusion flame. This is because this gaseous fuel, so the fuel that has vaporized and mixed with air, so both must diffuse into each other and then react. That's why it's called diffusion flame. And then this is some important consequence of this combustion characteristic. First is since the injection commences just before combustion start, so there is no knock limit here. So there is no knock limit. And then second one is that since the injection timing is used to control the combustion timing, so it is required that the ignition delay be kept short. That's why there will be a parameter that is used to determine the reactivity of this diesel fuel, which is called CTIN number. And then since the combustion process occurs within and around the fuel spray, so in this case, the engine torque can be controlled by varying the amount of the fuel injected per cycle. I already mentioned previously. And the next one is that as the amount of the fuel injected per cycle is increased, so you will see there is a problem in diesel combustion that we don't have in spark ignition engine combustion, that there will be a formation of the soot here. There will be a formation of the soot. That is one of the product of the emission in diesel combustion. And in this diesel combustion, because the combustion right after the fuel is injected, so we can set this combustion process under lean condition, which means that we can have a benefit in terms of the thermodynamic efficiency here. Now let's see the type of diesel combustion system. So generally there are two types of diesel combustion system. One is called direct injection engine. So in this case the fuel is injected directly into the main chamber. And then the second type is indirect injection engine. So in this case there will be a small chamber, so usually it is connected through a small nozzle or maybe couple nozzle, and then the combustion is initiated inside this small pre-chamber, and then the flame will propagate further through the nozzle, and then it will flow out to the main chamber, and it will be looks like a flame jet there. And this indirect injection system is usually used in small diesel engine. This feature is showing a different variety of the direct injection system. The feature on the left side, A, here is a direct injection system and with a quiescent condition, so no swirl, no tumble of the mixture inside the chamber. And then you can see there that there are more than one nozzle. So in here you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 nozzle here. And then on the B, you can see in here that there is a moderate air swirl here, and then the injector is also located centrally, but it is in slightly inclined. And compared to A, this B might have a smaller number of the nozzle. And then this roll is supposed to help enhancing the the mixing process between the fuel vapor and the air. And then on the right side here, it is operated under high air swirl. And special feature on the C, if you look at on the profile of the piston here, so the fuel is injected and then toward this point, and then the fuel flow will follow the feature of the piston. So some of the fuel will flow downward, and then some will flow upward. And if you see the feature of this piston in the upper side, so the fuel that move upward here will be re-enter into the center of the chamber, and that's why this piston profile is usually called as the re-entrant. So it means it is used to guide the fuel spray to re-enter into the center of the combustion chamber. So there are pros and cons of this re-entrance. Good thing for this re-entrant is it will help enhancing fuel air mixture, but compared to the open chamber on the system of A, so this re-entrance piston has a higher piston surface area, which is not good in the perspective of the wall heat transfer through the piston. So if you remember that the wall heat transfer here is a Q equal to H times A times delta T. So assuming it has similar H and similar delta T between the system of A and C, system of C has a higher A, so which result in higher wall heat loss through the piston surface. This is the example of the indirect injection system. So on the system of A, you can see in here there is a pre-chamber. It is at the top of the main chamber, and then this one, if you see here, this is a kind of a glow plug. This glow plug is usually used to assist the combustion of the diesel, especially during cold temperature. So for example, like during the winter. And then on the right side here, so it's similar here, but if you see here, the system on the right side, it has of different feature of the piston. And also if you see the shape of the nozzle, so you would expect no slow flow of the air inside the pre-chamber. But if you look at back the system on the left side here, you'll expect seeing a slow flow or tumble flow. It's depending on which axis we use. So the flow will enter the pre-chamber. I believe it will rotate like what I draw in blue line here. So, but if you see on the right side, the flow of the air will just enter straight toward this injector tips. And then this table is showing a different combustion type. So the first category here, if you see the size, so direct injection system is usually used for large engine. So in this large engine, because we don't need to have a very high combustion speed, most of the large engine, or not most, maybe some of the large engine are operated under quiescent condition with multi-spray. And then on the second column here is for medium size, so it is still with multi-spray and medium throw. And then for the small engine, because it requires a high combustion speed, usually it is equipped with a high swirl and multi-spray. And then on the right side you can see a system with high swirl and M type. I believe this is a special type of the combustion system developed by MAN. And then the next one is an example of the system with a pre-chamber, and then also the pre-chamber but with a swirl inside. And usually it is used for a small diesel engine. And then the next category here, based on the cycle, large engine is usually designed for 2 as well as 4 stroke operating condition. And then for medium and small engine, usually it is operated under 4 stroke. And then you can also operate the large engine with turbocharger or just naturally aspirated. S here stand for supercharger. And then for system with a pre-chamber, it can also operate it both. So either naturally aspirated, so without turbocharge, or turbocharged. And then you can see also the speed range. You know well already that for the large engine, usually it is operated under low engine speed. If you remember why, so because we need to maintain or we need to have a similar or maintain a same piston speed. So because large engine has a larger or longer stroke, we need to have a smaller engine speed here. And then for the smaller engine size, because the stroke is shorter, you can operate this engine at high engine speed. And then the next one is the bore, stroke, and so on. So if you look at next one here is the compression ratio. Usually a diesel engine has a higher compression ratio than spark ignition engine. You know well that there is no knock issue on this diesel combustion, so you can increase the compression ratio to have a better thermodynamic efficiency. And then the next category here is looking at the chamber. So for the large engine, usually it has an open piston bowl or shallow disc piston. And then for the medium diesel engine size, usually it has a bowl in piston shape. It might also has a re-entrant type piston bowl to enhance the mixing between air and fuel. And then for the airflow pattern, large engine, some large engine are operated under quiescent condition. And then for the medium and small engine, usually a straw is used to enhance the mixing as well as the combustion rate. And then next one is the number of nozzle holes. So for the large engine, usually it has more nozzle number than the medium and small engine size. For the engine with the pre-chamber, usually it has a single nozzle here. So this nozzle connects the pre-chamber with the main chamber. And then the last category you can see in here is the injection pressure. For the large engine, usually it has a very high injection pressure. The reason for this one is because you need to inject more fuel, and usually it has a slightly higher nozzle diameter. So to uh, enhance the atomization process, so we need to have a very high injection pressure compared to the medium and small engine, which usually have a smaller nozzle size. And then on next one you can see in here also the injection pressure for the indirect diesel injection system. So let's take a look into more detail about the diesel combustion right now. So because of the advanced technology, so we can now do study easily in this combustion process using visual tools there, so that we can see a fuel spray, we can see the flame behavior clearly, and then when we combine this uh, experiment type with the analysis of the engine cylinder pressure data, so we will have a better description of this combustion process. We can build a model for the combustion process of this diesel combustion. And then similar to the one in spark ignition engine, we can also use the concept of the heat release rate here to understand the diesel combustion process. So this heat release rate is obtained from the measure cylinder pressure. So it's the same as the one in the spark ignition engine process. And also recently simulation was also used massively to support the design and analysis of a diesel combustion system. So this feature is showing the record of the diesel flame on the left side on this A here. So this showing the flame from a single spray. So it's coming from the left side here. So this is for large diesel engine condition. So there is no swirl here. If you see on the spray direction, it just move simply from left to the right. There is no velocity upward or downward. So here the condition in which the spray is injected is at quiescent condition. And then on the B, you can see in here there are about maybe 3 or 4 spray there. Take a look here. Oh yeah, there are 4 spray here on B. And then you can see in here there will be a swirl, and the swirl is counterclockwise, so that's why it's deflected the spray counterclockwise as well. And then C here is example of the combustion system built by MAN, so they call this the M direct injection system here. And then next one, the last row here, D here, this is an example of the combustion with the pre-chamber. So looking at the size, I believe the pre-chamber is on the left side here, and then there will be a nozzle connecting the left chamber to the right chamber, and then the flame will propagate, exit this pre-chamber on the left, and then propagate into the main chamber on the right side. This showing the system that was used to record the flame on the previous slide. So on the system A, it is a quiescent condition, and it is a large engine with an open bowl, and you can see the schematic of the spray here. It has 1, 2, 3, 4. It has 10 nozzle here for the system A, and then system B, it has a smaller nozzle number. However, it's apply air swirl that enhance the fuel air mixing process, and the swirl direction is counterclockwise. And then system in C here, it has a different shape of the piston bowl. And then D was the one with the pre-chamber. So the pre-chamber is on the left side here, and there is a nozzle connecting the pre-chamber into the main chamber here. And then the next one, so this figure is showing the schematic of the fuel injection profile along with the heat release rate and the resulted cylinder pressure. So let's take a look first on the shape or profile of the injection process here. So it is represented by this line, the dash line. So this one is showing the profile of the fuel injection. And then as I mentioned to you at the beginning of this presentation, the combustion will start after a certain delay from the start of the injection, and this is the delay, you see. So the solid black line here, this one is the heat release rate. So you see here there is a spike of the heat release rate, and the spike you will see later on in the slide that this is because of the premix combustion, this spike, and then it will follow by a relatively low heat release rate, and this one is called mixing control combustion process. And then if you compare between the profile of the injection and the profile of the heat release rate, so you can see in here that the period of the heat release rate is longer than the period of the injection here. Then because of the combustion process, there will be an increase or the change of the slope of the cylinder pressure here. You can see in here it's change the slope. So, and this one is because of the combustion process inside the chamber. So looking at the on the chart in the previous slide, so we can see here that the total burning period is significantly longer than the fuel injection period, and then the absolute burning rate increases proportionally with increasing engine speed. So this is based on the test data as well as the simulation result. So this means that on crank angle basis, the burning interval remains essentially constant for different engine speed. So it's mean that at, for example, if the burning period at 1500 RPM is, let's say, 40-degree crank angle, at 3000 RPM, it's also about similar at 40-degree crank angle. And then the other characteristic that we have on this diesel combustion is that the magnitude of the initial peak of the burning rate in the previous diagram, so the spike of the heat release rate, this is depends strongly on the duration of the ignition delay period. So because during the ignition delay period, we have a time that's control the premix mixture, and this premix mixture will be burned, and this premix mixture burning control the spike of the heat release rate. So this figure is showing the schematic of the rate of the injection on the top, and the bottom is the rate of the burning. So in this case, the rate of the injection is broken down into several segments, for example, segment number 1, and then segment number 2, and so on. And then on the feature on the bottom side is showing the mapping of each rate of injection segment into the rate of the burning. So as you can see in here, there is also a dash line. So the mixture under this dash line is a ready to go mixture for burning. However, the ignition will start until a certain period here. So this one. So between this point and this point, it is an ignition delay. So the mixture that is injected and ready to be burned between this period of A and period of B, this will control the spike of the heat release rate. And then you can see also the burning timing for other segment, for example number 9. This is showing the burning on the segment of number 9 there. Okay, so this is a more detailed explanation about the heat release rate for diesel combustion. So let's start by the point A here. This is where the diesel is injected, so it's called start of injection or SOI. And then point B here, where we have the start of the combustion, SOC. Okay, so between SOI and SOC, we have a period here, which is called the ignition delay period. So the length of this ignition delay period control the level of the spike of this premic heat. And then once the premic heat ends, there will be a further combustion process, and this further combustion process is controlled by the mixing process between the fuel that is injected later and the air. Therefore, this combustion period is also called a mixing control combustion. And then there will be another combustion type here that occur late, so it's called late combustion period or late combustion phase. So let's take a look now a bit about the heat release rate analysis. So similar to the one in spark ignition engine, so usually we can get a test data of the cylinder pressure, and then we can apply the first law of thermodynamic and the conservation of mass to get the heat release rate based on the cylinder pressure test data. So this equation 10.2 is the first law of thermodynamic applied inside the diesel combustion chamber. So this is the heat transfer through the chamber wall, and this is the work to or from the piston, PTV, and this one is the fuel energy, so M times H. So H here is the lower heating value of the fuel, and then du over dt here is the change of the energy of the mixture inside the chamber. So when analyzing or when applying this equation 10.2, we can assume that temperature is uniform at each instant time during the combustion process. So this process will result in a net heat release rate, or sometimes it's also called apparent heat release rate, because in this case the heat release rate is lumped together with the wall heat transfer. So Back again to equation 10.2. I put this equation 10.2 at the top right side here. So if U and HF in equation 10.2 are taken to be the sensible internal energy, so once again it is similar to the one in spark ignition engine, then the dq over dt become the difference between the chemical energy or heat release rate and the heat transfer from the system. So in here we can write down dqn, and here stand for net. So this one is the chemical heat release rate minus the wall heat transfer, equal to pdv plus du over dt. And then we can apply the ideal gas formula here, and assuming also constant Cv, and then we can finally we can get equation 10.6. So in this case we can get the net heat release rate or apparent heat release rate based on the measure pressure from the test data. And then gamma here we can vary depending on the condition of the mixture, this is namely the pressure, temperature, and composition. So this picture is showing an example of the integrated heat release rate, and integrated heat release rate. So at the most top here you have a chemical heat release rate. So here you can see in here at the end, so assuming this is the exhaust valve opening, it doesn't reach 100%, and the difference here is due to the combustion efficiency. So there will be some unburned fuel at the end of the expansion stroke, and this unburned fuel might be an unburned hydrocarbon emission and then going out of the engine, or it might burn later in the exhaust process and in the exhaust system. And then next one you can see in here, this is the area here, this showing the portion of the wall heat transfer. So it can be about 10 to 15%. And then the next one here, it is the portion of the heat loss due to or going into the crevice, and then it will cool to the crankcase in terms of the blow by. And then this one, the line at the bottom here, is showing the QN. So this is the net or apparent heat release rate. So this is the chemical heat release rate minus the wall heat transfer. Next one, let's take a look on the conceptual model of direct injection diesel combustion. The feature on the left side here is showing the schematic of the fuel spray, and then on the right side is showing the corresponding fuel injection profile and the heat release rate profile. And then back again to the left side, so the dark color here represent the liquid fuel, and then the light dark color here represent the vapor. And then you will see also a dashed line that represent the diffusion flame, and then the dot point here represent the premix flame. So the first feature here is showing the spray at 1 degree after the start of injection. So ASI here stand for the after start of the injection. So 1 degree after the start of injection, the fuel is mainly still under liquid form. So this dark color, and then this is at 2 degree, and then at 3 degree after the start of the injection, the liquid that was injected earlier, it's already evaporate here. Some of this you see a light color there, a gray color. And then at 4 degree, so most fuel on the leading edge here, has been evaporated, and then 4.5 degree more fuel has been evaporated, and then at 5 degree you see now a dot point here. This area represent the premix combustion. So the fuel this has already been evaporated, so it's mixed with air, but still at rich mixture. V here can be between 2 and 4, and then because of high temperature, high pressure, it's ignite spontaneously, and then this spontaneous ignition generate a spike of the heat release here, and then further crank angle you still see the premix combustion, and then this premix combustion is followed by the diffusion flame. This diffusion flame occurs at the periphery of the spray, so this dash line. So this is diffusion flame, and then later you see there a bigger spray, and it's still surrounded by diffusion flame. And this one is, if I look at on the right side, this one is the diffusion flame. Okay, and then we can see in more detail about the structure of this flame in the next slide. So we can start from the left side. So at this timing, the fuel liquid is still injected from the left side, and then there will be a atomization because of the velocity difference between the liquid fuel and the surrounding air, and then the surrounding air, which is hot here, is entrained by this high velocity liquid and then entering the fuel spray form here. So at this region there will be a rich mixture with the V of about 4, and then going to the right here, this rich fuel mixture will also entrain the product of the combustion. So this one is just part of the combustion product, and the combustion was incomplete, so it still contain some reactive species, or sometimes it's called radical species, and then it will increase the temperature of the mixture further here from 825 to 1150, and then later it will increase the temperature at about 1600 Kelvin. At this temperature there will be a chemical process that release about maybe 10 to 15% of the chemical heat, and then this partly combustion mixture will move farther down, and then there will be a block of the hydrocarbon fragment here, and because of this rich mixture combustion and then also additional heat transfer from radiation of the surrounding gas, it will form a particle which is usually called soot here. So this is the zone where the soot is maximum, and then this piece here will move outwardly toward the diffusion flame here, and then there will be a diffusion process between this soot particle and then radical species and so on with the air from outside of the spray, and then there will be a further combustion within this diffusion flame front. So you can see in here there will be a rich premix flame within the spray. So in this one, and then it will be followed by a diffusion flame surrounding the spray. This one. Another feature of this diesel combustion is what is called a lift-off length. So this is the distance between the nozzle tips and the start of the combustion. So it is somewhere here. So where we have a premix flame. So this one, what is called lift-off length. Okay, so two important practical areas to be incorporated above a conceptual model of the spray, which can be used to enhance the diesel combustion process. First is, you might know already, is the air swirl. So this air swirl is usually used to speed up the fuel air mixing process, especially as the engine size is reduced, and then we need to have a maximum combustion rate due to higher engine speed. So let me draw a schematic here. So I have this top view, and then let's say I have 4 spray. Okay, so for quiescent condition, this fuel spray will just flow toward the liner, and then it will mix with surrounding air. And then if I draw the second one, and then in this case we apply a swirl. This is we apply the swirl. Then you expect that this fuel spray will flow like this one. Because of the swirl counterclockwise. So it's mean assuming you have the spray with certain cone angle, so you expect having more spray area because of this rule. So having more spray or larger spray area means we have enhanced fuel air mixing process. And then another important practical thing that can be used to enhance the combustion process is by having a multiple fuel injection. So instead of just a single injection process, we can have 3 injection nozzle, 4, 6, 8, and so on. For sure, the more nozzle number we have, the higher the injector price is. Next one, let's take a look on the fuel injection system. So this is the vital component of the diesel combustion, because through this system is the fuel is injected. So the fuel injection system usually supply a pressure of between 1000 to 2000 bar to make sure that we have sufficient fuel atomization. And then usually this injection pressure level depends on the engine size and the type of the combustion system employed. And then large pressure difference across the injector nozzle are required so that the injected liquid fuel jet will enter the chamber at sufficiently high velocity. As I mentioned to you, the velocity difference between the liquid fuel and the surrounding air velocity control the atomization process of this liquid fuel. So if we have higher injection pressure, it means we will have higher velocity difference, will result in also better or more enhanced atomization process. And then we can also have a different type of the combustion chamber to enhance this automation process as well. This picture is showing the schematic of the fuel injection system. So some of this you might be able to identify it easily. For example, this one is the fuel tank, and then number 6 here, I think it is a fuel filter. Number 1 here checks. On this one is pump. Number 1 here is fuel pump, and then this one looks like it's a sensor. Yes, this is rail pressure sensor. And number 3 here, this popular component, it's common rail. This is used to make sure that the pressure here are uniform, so that the fuel is injected uniformly between the cylinder. It's called common rail. And then number 4 here is pressure limiter. And then 5 here is the injector. So each cylinder has one injector. And then 8 here, I believe this is ECU. This is used to control the amount of the injection based on several parameters here, measured by several sensors here. Number 9 here is the engine speed sensor. Number 10 is the phase sensor. 11 is pedal transfer sensor. And then there is also a boost pressure sensor, V for sure, and so on. This feature is showing the detail of the fuel delivery system inside the injector. So the component here consists of the barrel, number 3, and then number 4 here is the plunger. This plunger can move up and down. And then number 1 here is the entrance of the fuel into the injector, and then number 2 here is going into the nozzle. So the level of the fuel flowing into the nozzle here is controlled by the relative position of the groove at the plunger here and the gallery entrance here. So on the first figure on the left side here, it is the condition where we have maximum delivery. So in this case, the fuel enter from the left, and then it's move up, okay, and then it's going into the nozzle. And then the next one, you can see that the groove that is at plunger here is at different position relative to the nozzle entrance here. So this is the condition where we have a partial delivery. So in this case, the fuel is still flowing from the left. Some of the fuel will move up, flowing into the nozzle. Some of the fuel here will move to the right. So this is partial delivery. And then on the most right figure here, this is where we have a zero delivery. So in this case, the fuel will move from the left, and then all of the fuel will move to the right. So in this case, there is not any fuel moving into the nozzle. And then on the bottom figure here is the mechanism to control the position of the groove at the plunger here relative to this entrance, this number 1. So it is controlled by this two-teeth rack here, and this rack movement is controlled by the ECU, and ECU control this movement based on several parameters, for example like engine speed, and then required load, and then V, and so on. This is showing the cutaway of diesel injector, and you can see in here several main component. For example, in this case you have number 8 here is the nozzle needle, and then the nozzle tip will be somewhere here. number 1 here is the pump plunger. So, and then the fuel amount here is controlled by this mechanism 14 and 15. So this one is camshaft, and rocker arm here control the moving of the plunger here. So the most important part of the injection system is the nozzle. So this is at the tips of the injector part here, and on the right side here you can see schematic of this nozzle. So for example, number 1, here you can see it is a throttling pintle nozzle, and then to A to B here is the side view and front view, and then number 3, this one is kind of hole type nozzle with a conical blind hole, and then number 4 here it's hole type nozzle with cylindrical blind hole, and then number 5 here is suckless nozzle. So suck volume here you can see this is suck volume. So right now there is a technology trend that try to minimize this sack volume, because this sack volume is one of the source for the unburned hydrocarbon. Because at the end of the injection, there will be a fuel remaining in this sack volume, and the flame won't be able to go farther inside the sack volume, which result in the unburned hydrocarbon at the end of the combustion process. This is another cutaway of the injector, but this one is electronically controlled. So you will see some electronic component in this injector that is used to control the amount of or the operation of this injector. So regarding the fuel injected amount, so in this case the amount of the injected fuel is controlled by the pressure difference. So in here we have m dot equal to cd. Cd here is the discharge coefficient, and then an here is the nozzle area. So cd times the physical nozzle area here equal to the effective nozzle area, and then rho here is the density of the fuel. So you can see here that this m dot is directly controlled by the pressure difference or the injected pressure. So if we assume a constant pressure drop across the nozzle and constant nozzle open area during the injection period, then we can get this total fuel mass by using this formula 10.15. So in this case, the total injected fuel is again a function of the injection pressure and the engine speed, this capital N. And then this delta theta here is the injection period. Last one, I would like to show you the diesel spray simulation using computational fluid dynamics or CFD. I think I've shown you this animation in chapter 1. On the left side is the baseline engine. So this engine has one injector installed at the cylinder head. This injector has 12 nozzles. So you will see 12 fuel spray from the nozzle tips. On the right side is the modified piston. So this new piston has a notch. So this work was conducted to see the impact of a different piston ball. And this piston ball is used to guide the spray and has a better fuel mixing process. So you see the pull-in piston and then the squeeze zone in this area. This animation is in terms of the equivalent ratio. So you will see a red color inside the spray. This is because of the rich mixture inside the spray. And then outside the spray will be a blue. So it's mean no fuel and 100% is air. And then at the spray interface, you will have a zone with the equivalent ratio around 1. So this is the zone where we will have the combustion. Let's play this animation. So on top row here is the top view. So you start seeing the 12 spray and then very red color inside the spray and then blue surrounding the spray, and then the spray hit the piston and then deflected up and down, and the combustion will occur in the zone where the equivalent ratio is 1. So this is an example of the research in diesel engine to design a piston for a better combustion performance. And the piston is moving down toward bottom center. Okay, we have completed the presentation of this chapter 10. If you have any question, we can discuss it in the next class meeting. Thank you. Stay safe.